Great. So today I'm going to discuss, me and Masazumi will discuss the effect of theta-angle of the Yamil theory on the lattice. So it is about numerical techniques to evaluate the effects of topology, if you like. So before starting, I myself have been working on this problem for the past couple of years. So these are papers in HEP lattice. It's numerical stuff. It takes some time to generate the lattice configuration, analyze, etc. So it actually takes some time. But this is a paper where we discussed the first analysis. This one, we introduced a new method. If you're interested in just looking at this, so probably there are way too many. So we just want to have a quick look at one of them. I recommend this one. It's a short paper and outlines the most new part. And then we subsequently have a papers about the finite temperature case. And interestingly, so for me, well, of course, this itself is, as I'm going to explain, it's a problem on Yamil theory and the numerical simulations. My personal motivation originally came from partly from my attempts to try to approach a confinement, starting from some perturbative explosion. There are some techniques known as the Borel resurgence, Borel summation, resurgence, etc. And then there's a question of how to put that into perspective. I approached that in one of these problems, and that was one of the underlying motivations. And I'm not really going to talk about that, but you'll see just a small implication of that during my talk. And then, in fact, this itself in turn came from my study about the inflationary model, actually. So, which still seems to be okay even after the update of the results. And then how to write down the potential relevant motivated me to ask this question. So somewhat interdisciplinary research. But let's see. So let me try to introduce the problem first, so that this is a very broad background. And also, I don't want to overload this too much information. This is towards the latter part of the program. So let's first introduce the problem itself. The problem itself is the four-dimensional pure Yamil theory. So with gauge group SU2. So it's old-fashioned theory. It's probably one of the first theories you ever encounter. So it's a pure Yamil, so there is no matter. And the gauge group is just SU2. You can ask, and there are some of the questions obviously generalizes what happens if you go to more general gauge group, SOSP, or you couple to matter. It introduces the interesting layer of structures. But as always in physics, it always starts with the simplest case. And in fact, there are some statements which are not often realized in this simplest case. But it's a simplest case, but for example, there is no supersymmetry. So it's still very difficult to analyze. And then I'm going to introduce the theta-angle to the theory. So the Lagrangian contains a term like 30 pi squared. This is okay, so Lagrangian contains a term like ff tilde, so f mu f wedge f. So in the standard physics notation, this. So this is the theta-angle in the Yamil's action. So and this is an extra parameter to the theory. And
is that, are there two pies?
Oh, sorry. Yeah, sorry. Sorry. Pi cubed. Sorry. Thank you. Okay, so somebody is actually looking at the blackboard. So let's see. So this is the Yamil's term. Sorry, a topological term, and it contributes to the, when you do the path integral, it contributes to the factor I and Q, where Q is the so this is also I theta Q, where Q is the topological charge. Which is an integral of this ff tilde. So if you just do the integral, you get some factor, and that's quantized, integral of the second term, and then this gives rise to this topological charge. So of course, this parameter determines how to weight different topological sectors. So we have a gauge field configurations, and it has several different connecting components divided by integer, and then this determines how to sum it up. So I'm sure some people in the audience knows about this pretty well. But just in case, and then and then by definition, so let's see. So what is the well, first of all, this parameter by definition should have a periodicity theta equals to theta plus 2 pi. So this topological charge is integer quantized, so that parameter theta should have a periodicity 2 pi. And then the interesting fact is that there's a tilde. So this is the term like electric field and magnetic field. So it breaks the CP in general. So the CP symmetry sends theta to minus theta. So at the generic parameter value of the theta, CP is broken explicitly by this Lagrangian. But of course there are exceptions. So broken, but so in general broken except at the special point. Of course, for example, theta equals to 0. 0 goes to 0, so it's fixed. But also it's like a pi. At least classically. So pi goes to minus pi, but the minus pi is equal to pi because of this 2 pi periodicity. So so theta equals to 0 and pi, at least at the Lagrangian level, is the CP symmetry. So that's one of the symmetries. So this is a conference about symmetry. So that's one of the symmetries we will encounter. Now, so this is the setup. Hopefully the setup is extremely clear. Now the question is, what is the dependence of the free energy as a function of theta?
Sorry, one more question. Are you going to consider here spin manifolds?
Well, let's see. Well, in practice, I'm going to consider on the torus, full torus. Because that's where I'm going to do the numerical simulations. Yes, but sometimes people can try to put a twist by different symmetries. For example, twist by center symmetries or things like that. So you can do a variety of options. And then of course, conceptually, you can try to do the more general manifold. And then of course, eventually I'm going to do on the lattice. And then there is a question how to do the numerical simulation of the lattice on the general manifold, which it has somewhat similar sounding talks. Through this program, so some of that may help. But so far, I'm going to talk about the more conventional ones on the torus. Yeah, so the question is, free energy. F theta as a function of theta. So the free energy is just a log minus log of the free of the partition function. So you can do the path integral and then define some partition function, and the partition. So it's basically that. If you like, you can normalize it and divide by the volume, etc. So that's just a normalization factor. So it's just really the standard free energy. And the question is, what is this function? So of course that tells you what the effect of theta is. If you take the derivative, you're going to get correlators of this term, topological term. Or some other context, this is not a parameter, it becomes a dynamical field, axion, which could play some roles in inflation or some search for standard model, beyond standard model, etc. And in that case, it's very important to know this potential, because theta itself becomes a dynamical parameter, and you have to keep track of the motion. And of course, that's severely affected by the shape of the potential. So the question is, what is this function? And I'm sure this itself was asked like literally 50 years ago or so. So this was introduced, in fact, David and collaborators in 1976. So almost half a century has passed, and then the question is there. Now, so the question is, what is this? What is the functional form? Of course, the function itself contains a lot of information. And one particular information which is relevant here is the fate of CP symmetry. So I said that the CP symmetry is present at theta equal pi in the Lagrangian level, but it might be spontaneously broken. And the question is whether that happens or not. So that's a well-defined question, another well-defined question. And if you know the shape of the potential, I'm going to discuss that, but you can tell that. Now, there is a related symmetry, which is this center symmetry, so-called one-form symmetry, Z and one-form symmetry. And this is Z and one-form symmetry. So in a traditional language, it was the center of the CSM, but it's more like a one-form symmetry of the theory, and magnetic one-form symmetry. And so this defines the confinement. In fact, in general, the definition of confinement is not completely obvious, but at least if there's a center symmetry, you can discuss. This is a sharp symmetry, so you can discuss whether it's broken or not. And if it's unbroken, you say it's confined. If it's broken, it's confined. It's almost like a definition in a sense. And then there is a mixed anomaly between these, which is at theta equal pi. So this is a classic work by Komowski, Gaiotto, Kapustin, Willett, Cyborg, sorry, maybe something went wrong. But yes, okay. Okay, maybe there is no Brian one wasn't there in that paper. Sorry. Okay, sorry. Okay, so there is a famous mixed anomaly. So at least one of them should be broken. So of course, both can be broken, but for example, if one of the symmetries is preserved, you conclude that the other should be broken, for example. So that also tells you whether the theory confines or not, which is of course a big business in the Yamyu theory.
Why can't it be gapless? Why can't it be gapless?
Well, yeah, so it can be gapless. Yes. So yes, it can be gapless. So in fact, in a discussion about the forum, so okay, so if n is very, very small, like 1 point something, if you try to analytically continue to non-integer values, which is questionable, but if you try to do that, you might land on something like that. But yes. Yeah, but anyway, I think, yeah, so if you like, I just, yes. Yeah, so let me hear just formulate the question of symmetry itself, yes. Yeah, and so that's the question. And yeah, so which is fairly standard, I think. And in fact, if you open the textbook, it seems that people don't necessarily talk about sake of pi in particular, but there is a very standard answer as to this function in the textbook, in some of the textbooks. And in fact, so there is an Instanton computation, so-called. Well, so there is an Instanton contribution. So there is a semi-classical analysis you can try to do. And there's one instanton, two instantons, but you can try to do the one instanton calculations. And then you can try to evaluate this function. That's the classic Hooft result. And then the free energy, it says that the free energy takes the form of 1 minus cosine theta. Or at least a cosine periodic function theta. Which sounds very plausible. And in particular, it's a clearly periodic function of 2 pi, period 2 pi. And there is a maximum of theta equal pi. So there is a, like this, theta equals 0, theta equal pi, there is a maximum. But nothing funny happens with theta equal pi, except that it's a maximum. So that's a standard answer. And if you look at the literature, people keep quoting for example, about the inflational models and everything, people keep quoting the answer result. And in some contexts, that's a true answer. But in general, it's actually subtle whether this instanton result gives the correct result or not. And that's related to the fact that so instanton classically is a scaling invariant, so there is a modulus, the size modulus of the instantons. And then there is an integral. So dimension reason for reasons, there is a coupling constant, g squared or so. But then the coupling runs. There is a one loop running to the coupling constant. so there is a factor rho, but then introduce a scale because you're doing the learning, and there is a relatively large factor, 11/3. So this is the coefficient of one-loop beta function. And in fact, as I said, this factor is relatively large. So even for n equal 2, it's 7 or so, which wins against this factor. But unless you analytically continue n also, so there is a IR divergence. This one has an IR divergence, namely at rho goes to infinity. So when rho goes to infinity, this diverges. So this is actually a very dangerous integral in general. So there are a lot of issues like this now in the literature in various contexts in field theory, especially in thermal field theories, where there is IR divergence, and you have to IR problem, sometimes people call it. And in those contexts, you have to be very careful about this expansion. And in fact, I'm going to argue that in fact, people, including Witten, for example, argue that at least in some contexts, that this is not valid already in the 80s or so. So in that sense, it's known that this is not always true, but whether people appreciate that or not is a different question. But anyway, so this is one canonical answer. It's a cosine. Well, of course, if you go to 2 instant, you have cosine 2 theta, 3 theta. But anyway, whatever it is, it's going to be a periodic function. That's what people believe. But that's not, in general, that's not necessarily justified. So then the question is that what is going to be, so in fact, whether this answer is justified or not depends on the matter contents really. If you have quarks, it might depend on the mass and everything. But let's see. But today I'm going to talk about the Yamazaki theory. Now, what could be the other possibility? Yes, that's right. So indeed, a lot of the insight. So before I started doing the numerics, obviously I was interested in trying to go as far as possible with analytical methods. And then, so indeed there is a large N analysis, some of the analysis was lying in the strict large N limit, and then there is then I tried to incorporate story to finite N. Not strictly large N. That's what I try to do. So now, what is going to be the function? So let me tell you my conclusion. Well, at least that's what I believe, and there is some evidence for that. But let me first write an answer. So first of all, so this is f theta. At theta equal to 0, you in general expect that there is some minimum, local minimum. And so that's and in fact, close to here, f theta has expansion. Maybe it's better to write here. Pi theta squared, 1 plus e4 theta squared. So it's a high. You can expand around theta. And then people in general expect that this is the minimum. There is an old paper by Buffer Witten kind of argue for that. That this is the minimum. But anyway, I'm going to do the numerics, and then the fact that this has a positive curvature, you can check. In fact, other people have done it in the old days, and I don't think there is a dispute for that. Now, of course, another comment is that there is a CP symmetry. So there is a theta to minus theta, so there is a Z2 symmetry. So you can you can think about only the positive part if you like. And in fact, what some people, I think, with them argued is that in the larger limit, you can do the scaling. And in the larger limit, you actually get quadratic function. And in fact, that's already an interesting observation, because if it's a quadratic function, then it's obviously not 2-pi periodic. So let's see. But let's see, sorry, maybe before coming to that, so it starts with a quadratic function, and then you try to incorporate you try to discuss the finite N case. And it keeps going, but at least at some point it should saturate somewhere. It shouldn't keep growing quadratically because it means that energy goes random to infinity, which sounds very bizarre. There should be some cutoff scale, and then there is a natural scale, which is like a dynamical scale of the theory. So roughly speaking, it should be that there is a scale. There is a scale, lambda to the fourth, and then it should be bounded by something here. Because that's the only scale of the theory. There, you can observe the numerical coefficient. So, and then there, the plausible possibility is you approach somewhere here, so that it keeps bounded. So at least it's a second derivative positive here, but it should become negative there. And in fact, of course, how it approaches, etc., is a widely open question. Well, interestingly, people have tried to look into this potential using holographic methods for some so-called holographic QCD, which is holographic pure Yang also, in fact, which is not the pure Yang theory itself, but more like a deformation. In that case, people could compute this potential, and it takes that form.
Yeah, but it is not 2 pi periodic.
Yeah, that's right. So I'm coming to that. Yes. So that's it's not 2 pi periodic, which looks very, very funny. Now, what it means is that when it comes to pi, of course, there's in order to make this 2 pi periodic, of course, some other things should happen here.
All right.
So, what happens here is that there are multiple branches, and of course, the physics. If you go back to the Lagrangian, obviously it's 2 pi periodic. So, you want to, for example, look at the minimum energy state. You should look at this branch. Well, in fact, there are multiple branches. There's another branch, etc. But if you try to look at the minimum energy branch, it's like this. And then, in fact, thank you for asking that. So indeed, there is a cusp at theta equal pi. So because this is 2 pi, so this is right in the middle. And in general, it's a non-trivial function. There is a cusp at theta equal pi. And that means that the CP is spontaneously broken. So that's the non-trivial statement.
Why are you relating the fact that there is a cusp with that is breaking CP?
Well, let's see. Because so because there is a discontinuity in the state. So in a sense, this gives this. There are two different type of gauge configurations which gives rise to this, or states, if you like, vacuum, giving rise to this branch and that branch, and they are very different here. But they kind of coincide there, and then they branches off again. And I take that as the root definition of the transition. Yes.
Is there some quantum number that is able to differentiate?
Let's see. Well, well, let's see. Let's see. Yeah, I think the answer is yes, but let's see. Can I articulate that now? Yeah, I mean, let's see. I'm not sure I can say it now. Sometimes you can dualize this axion field, and then there is a flux of that dual field, and which people discuss, which plays a role similar to this branch. I think that's a roundabout answer probably, which I hope is correct. But I might look for more cleaner answer. But yes. Yeah, so that's the thing. And in fact, even the Lagrangian limit, so we can also argue that in the Lagrangian case, we can argue that there is a quadratic function, and it's not 2 pi periodic. Of course, the same reason if it goes quadratically, and then there are metastable branches. And it seems that I talked with a lot of people, and then so certainly this was discussed in the old days, but I talked with a lot of people, and sometimes people are upset there are metastable branches. The branches look unphysical or something like that. So it's fair to say that meaning of this unstable branch is not completely understood. But the question is, but anyway, I think the question is, at least this raises the question that theta equal pi, at theta equal pi, CP may be actually broken. And then that related with the branch structure. Well, of course, another related question is that if there are multiple branches, for example, for pi and etc., and then there are, if you keep shifting it, you might conclude that there are infinitely many branches, which is true, I believe, in the Lagrangian limit. But I believe that we have an argument, but in general, if you have a larger limit, it should be that this comes back to 0. Even one of the branches should come back to 0 at 2 pi n. So that's the statement. So claim is n branches for SU theory. And we're going to see the numerical evidence for that in the following. Well, for example, if you supersymmetrize it, there is a super Yang-Mills. You can check the n branches, and then maybe you can try to deform back to supersymmetric Yang-Mills. Sorry, non-supersymmetric Yang-Mills, and it's n. And in this paper with Yonekura in 2017, we argued for that using the connections for some deformation of the CPN model, et cetera, et cetera. So, but anyway, so there is a question of how many branches and what is the branch structure? Is there a cost to theta equal pi? And the question is to see that. And so, as far as I see, the numerical technique is the only way to really tackle that. I mentioned that there is a holographic technique which certainly works in some limit. There is an argument of mixed anomaly, but of course mixed anomaly says that either should be broken, at least one of them should be broken, and but it's hard to go beyond that. Maybe both are broken always or things like that. So it's hard to go beyond that. So that's what needs to be discussed. And before coming to the slides to talk about numerical results, let me have one more comment. So here so far I discussed the general n. And in fact, for this discussion, people try to start to approach the large n limit. N equals 6, 7, 8, etc. Large n limit, there is a numerical combinations. But actually, to some extent, I want to talk about the case of SU2 Yang-Mills theory. And in a sense, that's the most interesting case.
Yeah, for question.
Yes.
In 2 dimensions, if I remember correctly from the expression of the free energy as function of theta, you can extract things like the string tension.
Yes.
There's some interesting observable that you can extract in 4 dimensions from function expression.
Well, let's see.
You mentioned something like tension of domain walls.
Yeah, I mean, in fact, I'm going to discuss, in a sense, somewhat similar to that, because I'm going to, in the part of the numerical techniques, I'm going to make a region where the theta parameter is different from some other regions, and then there's going to be a tension.
Oh, okay.
Yeah, in fact, that in my presentation, that comes along the ways of technical thing, but I think, in a sense, we also computed that quantity, tensions of regions with very different value of theta.
You can tell that vary from 0 to 2 pi.
Yes.
You generate the domain walls.
Yes. And in fact, that quantity will appear. Yeah. Okay. I don't remember if you have a protonut, but that will appear in the formula as a byproduct of analysis. Yeah. For example, that's an interesting quantity. If you change the theta, if you change the theta everywhere, then yeah, it's more like correlate. If you take the derivative, it's correlate of FTF derivative. So, which itself is an interesting quantity. Yeah. If you go to Yang-Mills with matter. People are interested in those quantities because of the people trying to understand the eta mass, eta prime. Sorry, I forgot the mass of this particle. So there are some phenomenological motivations. But let's see. But before coming to the numerical results, let me write down one more figure. So I here write down 1 over n, or 1 over n squared, if you like. And then okay, maybe I'll write it a little bit lower. Oh, it's okay. Yeah. So and then there is a 0, so which is like n equal to infinity, and then there is a different value, n equals 3, n equals 4, all the approaches to n equals infinity. And so in the larger limit, you can do the larger analysis, and indeed you can argue that you can just write on the function it's quadratic, and there are multiple branches. So when I go to large n limit, so this is large n, then in this region CP is spontaneously broken. And in fact, in this region, people believe that the one-form symmetry is not broken, which is consistent with a mixed anomaly. So either should be broken. And so here is the confines. So let's still talk about the Yang-Mills, 4D Yang-Mills at theta equal pi. And here, it's there is well. So the question is that what happens all the way here, and in fact, the useful analogy people often invoke in the literature is the 2D CP N-1 model at theta equal pi. Well, in fact, this is supposed to be CP N-1, not CP N, because in fact, CP N-1 has a ZN symmetry, which plays a role. It's a ZN flavor symmetry, but which plays a role similar to this ZN here. And in this case, that's, well, to what extent it's actually rigorously shown or not is a matter of debate. But in this case, people often say that n equal 2 is special. N equals 3 or so. But then there is a sharp transition in between. And so this point is related with the Haldane conjecture also. Again, I'm sure some people know about that much more than me. And then here you can discuss a similar story. CP is spontaneously broken, but in this case, there is a CP. And then here it's the confines. So here there is a gapless mode. So this is the gap. And then there's some transition in between here. That's the structure people know. So n equal 2 is very special, which is not too surprising because it simplifies the larger limit. So n equal 2 is the farthest away actually. So something might happen along the way if you try to extrapolate.
But here, there's a good reason that in 2D, there's a good reason this happens, right? So the argument is that in UV, you have Zn and CP symmetry. You want to match some anomaly.
Yes, yes.
And the candidates are some SU1 and level 1 WZ.
Okay, yes, yes.
Yeah. Then the question is, when the flow goes close to the SU1 and level 1 WZ model, are there relevant operators that might potentially be triggered when you go close to the fixed point? Now, it's a very simple WZW model analysis that shows that when n is 2, all the relevant deformation near the fixed points are forbidden by the UV symmetry.
Okay.
But when you go to SU3 at level 1 and higher, there will be symmetric relevant deformation. It's not protected, and therefore trigger a further flow.
Okay, yes, yes. So
the fact that if you look at SU1 and level 1, the WZW model representation theory, when n is large, you have more relevant operators.
Yeah. I think so. So yeah. So in fact, if you can invoke the like West-Minowitten model description, then you can analyze the deformations and come to the conclusion. Yes. And so indeed, here in this case, of course, there is no sharp argument like that. Well, let's see. So there are various different things you can say about this. In fact, first of all, in the old days, people tried to, in fact, one of the motivations people started thinking about CPN models, of course, to study 4D Yang-Mills. So, and because of that, they suggested, so they tried to analyze CPN model and learn about extract lesson for 4D. And in fact, there's a nice paper by Shankar and Lee in the 90s. And who said that in view of the remarkable similarity between sigma models and four-dimensional SU2 Yang-Mills theory, it seems very likely that the latter is also massless at theta equal pi. So don't blame me, but which sounds like a very reasonable thing to say. So, well, of course, then there you can try to do, except that here, for example, already here, people notice that SU2 is actually special because so n equal 2. So you can look at the universality class, and if there is a critical point, and in fact, for the Yang-Mills SU2, there is a Z2 critical point, which is the Ising universality class in 3D Ising model, and that's not to be second order phase transition. But people believe, partly because of the analysis of Potts model and all that, and partly because of the lattice simulation, people expect that these are supposed to be first order transitions. If you raise the temperature. So So indeed, the order of the phase transition is different actually here. So that's one indication against the possibility that n equal 2. For the possibility that n equal 2 is special. N equal 2 is still seems to be trivial. It's different from others in the order of the phase transition. Of course, that's just the only evidence. Now, you can try to really connect the story of 4D to 2D. And then the story is, of course, never completed. But there is you can try to do it a little bit. For example, you can compactify first 4D amines on the torus. And then there's some extra degrees of freedom, which originates from the fields of the T2. And so this is this is a little bit digression, but if you have a two-dimensional torus and you do the amine theory, it's the action is f squared, so you have to solve f equal to 0 roughly. So there is moduli space of Rat connections. And then, for example, if you take SU2, it's a T2 divided by Z2 times Z2 also, which is like a pillow case, and which is topologically, well, we shouldn't say topologically, but if you roughly speaking CP1 plus singularities. And in fact, in general, you get CP N-1. So you get the version of CP N-1. In fact, Atiyah has a related paper. But also, there was a question of whether you can really take advantage of that to try to connect this discussion to there by taking advantage of that structure. Well, of course, it's not the CPN model. The metric is different. There are singularities, etc., but you can try to connect that, and that's what I try to do in some other paper. So, let's see. But of course, in that analysis, it was clear that there is a relation, but you have to do a lot of extra operations. The series are not exactly CPN model, and there are a lot of singularities. Also, the regions, there is a lot about argument how to compactify this circle, that circle, and then change the relative size, etc. So anyway, regardless of details, you have to analytically continue from here to there all the way, and something might happen along the way. So there are relations, but it's not clear what happens here. So the question is that there might be a line between, but so there might be a line where this is the CP is preserved, Zn is broken. There could be a region both are broken in the middle. But there should be at least some boundary, at least minimally one boundary between the two regions, and then is it here or there? That's a sharp question, and because of that, SU2 is the most interesting case. Yeah, so that is the motivation. Sorry, maybe I was a little bit too slow, but so that's the motivation. And let me try to show you the results. Oh, sorry, thank you. Yes, I need to turn off the lights. Let's see. And then I have to click. It's a little bit hard to see. Or maybe, oh, sorry, I have to see the cursor. Where is my cursor? Oh, okay, here. And then it's here. Okay, great. So, and then basically I'm going to do lattice simulations. And I'm not going to talk about too much details, but first of all, the idea is to discretize everything. Put the theory on the full torus. So I'm going to do the Lagrangian simulations. So not the Hamiltonian formulation, which is an interesting subject in itself, but I have a Lagrangian formulation. All the space-time is discretized to a lattice, and for each lattice there is a SU engaged field. Everything is finite, and then the partition function, etc., everything is well defined, and it involves integrals with many, many variables. So if you try to do it naively, it certainly cannot. But there is an interesting Monte Carlo techniques where you can evaluate that by essentially taking out important contributions. And that's the subject of lattice case theory, which people have developed. Now, here I want to include the effects of the topological charge, which is the integral of f tilde. And then the way to compute that is not too difficult. So, just the pointer or not. Yeah, so, okay, maybe it doesn't work. Okay.
The lattice topology of T4 or?
Yes. Yeah, it's really periodic in all directions. So typically people try to change the spatial size to be the same, and then change the temporal size. And that plays a role of changing the temperature. And in practice, how large? At least in my simulations, typically 24 cubed times 48, for example, or sometimes I go to 48. But if you go to 100, yeah, 28, it's very serious computation. So it depends on how much computational resources you have, etc. But so for each edge, there is a link variable, which is like a gauge field, Wilson line in a sense, transforming under the gauge transformation on the both ends. And then there is this bracket which goes around, which is a gauge invariant because it's a closed loop. And roughly speaking, if you just evaluate that, it gives this F. That's what's written here. But in practice, for example, you want to evaluate first, measure the topological charge density. So you take a point X, and you take an average over the all possibilities to make it symmetric. So there are four, not four, sorry. In this picture, four, but in 4 dimensions, there are more directions. But so, yes?
The binary function has a I inference, like if
yes,
you
yes.
like to, his library has sign problem,
yes.
How do you better that?
Yes, yes, very good question. In fact, I'm coming to that in probably next slide. Yes, and yeah, so that's in fact the whole problem in a sense. That's how to. The problem is definitely there. So the question is what to do with that. And then basically you have to invoke some extrapolation techniques. So in Fedorov method, you at least in the Lagrangian formulation, you do the computation on some other regions where sign problem is, I wouldn't say not present, but sign problem is better. And then try to extrapolate back. That's going to be the strategy, more or less. But of course, that's a subtle question, whether the extrapolation is good or not. And sometimes you just have to do it to see whether it works or not.
How do you know this works? So we need to compare exactly.
Yeah, in fact, hopefully in the last 20 minutes or so, I'm going to show some evidence that some particular extrapolation scheme is working well. Yes, and then indeed that's in fact, thank you. That's going to be the whole point of the rest of the slides. So I'm going to some plot but of course it involves the extrapolation, so you have to be careful. Except that, but the extrapolation itself is actually not bad. In fact, in almost all the lattice computations, people typically extrapolate anyway. For example, there is a discretized on the lattice, for example, and you have to take a continuum limit or something. Even the very simultaneous computations, quite often, not always, but almost always, you have to extrapolate anyway. So as long as things are under control, that's completely okay, I think. But of course, that depends on particular details of the scheme. And yeah, so okay, so indeed, maybe I should come to that, and instead of talking too much about this, but at least that if you just want to measure FF tilde, there is a way to define F mu nu on the lattice. First of all, this is the most naive thing, and then just discretize it and put it in the lattice, and then evaluate it. And then you can compute this topological charge density. That's the most obvious way. But first of all, there indeed, even before coming to the sign problem itself, there are a little bit of conceptual questions. So if you define it in the most naive way, topological charge is definitely not going to be an integer. Which you might imagine it may be okay, you're going to take the limit, etc. But the fact that it's an integer, etc., is so crucial, or at least close to the integer, is so crucial for having this phase and everything. And then the reason that it's not the integer is that it's because it's on the lattice. So if it's a smooth configuration, you can say that it quantizes. But on the lattice, you can have a very, very discontinuous configuration. Like here in this here, I have plus minus 1 for Z2 field, where there is no continuous field counterpart. And in these configurations, definitely, there are widely fluctuating fields, and the topological charge wouldn't go to integer. So on the lattice, there is first of all, intrinsic question of whether it's not an integer. Now, this problem people have discussed quite a bit. And one is to introduce some version of the fermions. And people call it overlap fermion too, and use a version of the index theorem, which is not unrelated to like the so-called Ginzburg-Wilson fermion. So some version of the index theorem on the lattice to try to define it by integer, as an integer. Which is the most elegant way, but unfortunately, for me, practically, it's a little bit computationally costly. Because you have some fermions and the signs and the determinants and all that. So there's a little bit more. Yes.
First, there is a very good point.
Yes.
How are you going to enforce whether the theory is SUN gauge theory or CP SUN gauge theory?
Well, let's see. So here it's very right. So here it's very well. So depends on. So here we are going to discretize everything, and the question is how to. Yeah, let's see. Well, let's see. So here I'm literally integrate over the say, for example, SU2 gauge field, and if you want to, for example, do the SO3. You have to include some extra structure. Well, for example, one way is to, yeah, I think you have to include some extra structure to the action to make that well defined. Yes.
SO3, then you can also take alt integer values. So you are going to integrate also over configuration in which Q is not integer but it's alt integer.
Okay.
So, but here it seems that, I mean,
yes.
It is built in that Q can take in principle not integer values. So I'm a bit confused by how do you choose the global structure of the values.
Let's see.
Presumably, the lattice field configuration key in the thermodynamic limit over.
Okay.
Yeah, I mean it ultimately depends on how you generate the lattice configurations. Yes, and so that's going to be the difference, I think, and yeah. I think there are some papers who did the SO3, for example. Yamazaki and the lattice. I always try to avoid discussing that because here I'm a numerical theorist right now, and each time when I try to change the setup, I have to play around with messing around with the code and waste several months of my time. So I'm a little bit conservative when I do numerical computations. But yes, conceptually it's an interesting question how to do it for general. Yes, SUM of ZN. Or SN of ZM, for example, general M.
I thought it was a known problem that there's no good way to include the topology of the group, of the non-obedient group on a lattice, because bundles on S4 have a Chern class, a second Chern class that determines the topological type, and that I thought forces a quantization of Q. On the lattice, you don't see that, so it's a known problem.
That's right. Yes. So that's what I'm talking about, more or less. Yes. Yeah. So indeed, it's not discretized. So, for example, what people have shown is that if you impose the condition that the gauge field is not too widely fluctuating, some inequality, and then integer quantized, for example, etc. But you have to extrude some configuration of the lattice to make it well defined. Indeed. Thank you. Yes. And that's a problem conceptually. But the point is that there is a way to go around this practically somewhat. And that's called there are different techniques. So, but let me say, for example, one is called a smearing technique. So the details doesn't matter, but basically, if it's too widely fluctuating, that's dangerous. So if you kind of smear it one way or another, that it makes it better. And here, for example, you take compare with others around it, and then replace it by the value determined by other neighbors, for example, so that you get along better well with your neighbors. Talk to the neighbors and then decide what you're going to do. So that's the sun smearing techniques. The concept, there is a better technique known as a theoretical better technique known as a gradient flow. It's like you write on some sort of a diffusion equation and let it along the flow, and then it becomes more smooth. So it's sort of partly a black magic, but first of all, there is a way to make it smooth. And in fact, it works. So this is how I tried. So in the original, if you just generate it and measure the topological charge, this is what you get. Here are several different values of parameters. So not at all the integer, which is not too surprising. If you just measure the topological charge, but there is some smearing procedure, whatever it is. And if you just repeat it, like 20 times is reasonable enough, 100 times or so, there is a sharp peak. everywhere at the integer values. So there is a very well convergence to integer. And then, in fact, you can also do the smearing, how smearing works more practically. So this is an example of the plot of the topological charge density. So there is a smear. So there is a smearing step coming from left to the below, and then it makes it more smooth. When there is a lead, there is a high concentration, but it's smeared out. Well, of course, as you might expect, if you do it too much, then it smears out too much. Because so you have to you shouldn't do it too much. Okay, but that's how you define topological charge. Now there's a question of what you're going to do with this sign problem, because there's a factor of I, which is the most important point. And then so let's see. So the method we propose is the follows, which is again very numerical. First measure the charge, etc., so that it's integer. Now measure the topological charge density only in some regions, not in the full region. Say half of the regions. And then measure the charge in that region, which is not an integer, because it's part of the region. And then the fact that it's not integer makes things good, at least better. Because if it's an integer, it's widely fluctuating, plus minus. But if it's a little bit away from the integer value, so it's a little bit better. And then do the numerical simulations there. And then there you take some regions in the space, part of the regions, there is a control, so where you can do this controlled computations, and then try to analytically continue back to the whole region. So that's what is, yes, the method.
For CP1 and theta.
Oh, yes, that's also a very good question, indeed. Indeed, that's a very good question. In fact, a version of this was already interestingly done already in 2008 by these people. So in that case, it's 2D. So so you have theta. So in a sense, you have a small region where there is a region of theta equal pi. Or integrate the parts, you turn on the Wilson line in some points, and then people, these authors do the computations, and there is a very clear difference between CP1 and CP2 and larger, CP5 and 9. So CP1 case, it comes back, which is consistent with the discussion. For CP5 or not, it just keeps going. It's there are error bars, but it's very clear that it doesn't come back. If you go to CP9, it just keeps going clearly. So it's not clearly 2-pi periodic. So that's already there for CP N model. And it worked in that case. And our method is, in a sense, a 4-dimensional generalization of that.
I didn't get the work. Wouldn't you expect it to be periodic, irrespective of Cn for any?
Well, it's eventual. So in a sense, here, the statement that what we are plotting is supposed to be a single branch. Yes. And in fact, it's not unrelated to the fact that when you change the value of the theta, in fact, I'm not changing the lattice gauge configuration itself. So I'm generate the lattice configuration theta equals 0, and then use that lattice configuration to explore the dependence on theta. Yes, and of course that's not good if you want to find the transition itself, because then you have to change the lattice gauge configurations. But actually, what we want to do is keep track of single branch so that we can see the multi-branch structure. Yes. So that's the case for CP N model. Now, and then so the discussion is very similar. So because there was a question about tension, etc. So this is I already said that in words, but this is more in the equations. I take a small subregions where only in that region I have theta equal 2 pi. And then there is a size of the subspace L. And then the free energy, I compute the free energy, and then extract the dependence on L. So I want to take L to be large. So I fit this as a function L as this leading term plus the domain of tension, which is what you were asking about, plus subleading corrections. And And so this should work in practice, but of course, whether it works in practice or not depends on how small this is, or whether there's a good region where there's a linear in the inverse size, which a priori I don't know. But the thing is, it's try. Oh, sorry, it's already time. But let's see. So, and then this is one of the plots. So this is 1 over L. So large, I want to extrapolate to L equals to infinity, which is L equals to 0. And there are some, so there is a different value of theta, but and there are some errors. Errors are in this plot so small, but you can try to extrapolate. And if you come too close to here, the error bar becomes too large. I haven't eliminated the sign problem. So, but at least here, error bar is small, so you can just, and then you try to fit that in the linear function. Well, you can try to change the function a little bit, but the actual conclusion of whether it's 2-pi periodic or not doesn't seem to depend too much on details of the extrapolation. You can fit with more crazy function, but anyway, that's, so the extrapolation seems to work pretty well.
May I ask a question?
Yes.
Are you doing this extrapolation while fixing full volume?
Yeah, so the full volume is fixed, yes. Full volume is fixed because I generate the configuration with some already prescribed lattice. Yes, 24, etc. And then of course I generate different things with 36 or so, but here in this plot I have fixed the full volume and then just change the subvolume to make it first. First, that's the first thing to do. Yes. And then you can try to extrapolate the value. And then setting aside the details, okay, so this is what we got. So this is theta equals pi, again, SU2 theory, and temperature 0. And then, sorry, there are too many plots, but basically there's just this thing. And then, so this is the cosine. If you try to, okay, depends on how you write the cosine, but you try to fit here with the quadratic piece and write on the cosine. But here it's a result, and it's clearly not 2-pi periodic in our opinion. So yeah, it's a lattice paper, so you can try to discuss like there are some systematics or so, but even if you have a systematics and put it a little bit up there, I don't think you can dispute the fact that it's not 2-pi periodic. Error bar is surprisingly small. Of course, it depends on how you estimate the systematics, but I thought that we did a reasonable job. And in fact, interestingly, you can try to fit even better. And in fact, sorry, again, there are too many plots, but there is this line which seems to fit the data well in the middle. And that one is actually cosine theta over 2, which is a big surprise. A priori, there is no guarantee that it's just cosine theta over 2, which is in particular 4-pi periodic, not 2-pi, but 4-pi. And that's consistent with the expectation that for SUN, there are n branches, which I mentioned before.
Is it all related to whether or not the spacetime has a spin structure?
Spacetime has a spin structure or not? Well, no, but let's see. I would say that, well, related. Well, it's a property of the theory itself, I would say. Maybe your question is that suppose that you put the theory on a manifold without a spin structure, for example.
You said like a lattice. I don't know what a spin structure means.
On the relative factor of 2, you have in mind is there U1, but not for U2.
Okay, yeah, I know. I only know it's there for U1. Yeah, I was wondering.
I don't think there is.
Yeah, I'm doing SUN. Yes. Yeah. Right. Okay, so this is the, in a sense, this is the main result. Now, yeah, let me spend, sorry, about 5 more minutes to talk about the final temperature. 2 slides. So now that you have that, you can discuss the final temperature theory by basically changing the size of the temporal direction. And in particular, you can vary the temperature and see, look, so you can try to discuss the dependence of the critical temperature, confinement to confinement transition temperature as a function of theta. And you can derive that, and if you have a fit, it decreases quadratically. So that's the result. And yeah, there are some discussions people try to have in some different series where it decays quadratically, for example. But I don't think there is a way to know the value, for example, otherwise. Now, the other point is that related to what Masazumi was asking, that for example, now you have a finite temperature. You can discuss the critical temperature. And then you can discuss the version of universality. And the statement of universality is that, so here it's a protein Binder accumulant or so it's a quantity which extrapolates here and there. So if it's 0, it's one phase. If it's 2/3, it's other phase, and there is a transition. And if you change the lattice size, there are 3 different lines, completely different lines. If you regard as a function of temperature, so this is the deviation from critical temperature. But if you try to scale it, depending on the system size, 3 different lines actually converge very nicely to a single line. And this is what is expected from universality of the critical point. So you can say that this is a check of the universality, but also it's not like I'm in suspicion of the 3D Ising class. So it's maybe it's more fair to say that this is a check of the extrapolation scheme, sub-volume method I'm using. So if I did something nasty, it shouldn't be that they converge nicely to a single point. But it's just we follow the procedure and just plot it as a function together with this particular critical exponent, knowing the literature, and then everything collapses to a single line. So it seems that we recover very well the universal behavior of the critical point. So that's another consistent check of our procedure at the final temperature.
NS is the number of sides.
Sorry. Spatial direction. Spatial direction. Sorry. Yes. Spatial direction. And T is the deviation from critical temperature. So yeah, you're changing the temperature from below to above. Yes.
Is it fair to say that the sign problem due to the theta term is somehow more crucial at close to 0 temperature because higher temperature and
yes,
things are washed out. So even if you mess it up, it won't matter so much.
Yeah, definitely. So that's indeed the case. And for example, we did a numerical simulation at above the critical temperature, for example. We used exactly the same method, and it actually coincides with one cosine, etc. So indeed, some of what people said is definitely correct. Like if you go to high temperature, like a Gross, Pitarsky, Yaffe, they have talked about the final temperature, etc. So that conclusion that you have a cosine at high temperature is generally correct. So the question is what happens if you go to the lower temperature and what is the shape? So yeah, that's the end. Thank you.
DC was going to 0 and theta equal to 5?
Well, let's see. It's not completely clear. Yeah, indeed, I was interested in that, and yeah, we don't have a definite conclusion yet from the numerics. But yes, it definitely approaches very close to 0. But whether, yeah, I might have some speculations, but yeah, at least I need to have more numerics to verify that. I mean, unfortunately, when it becomes very close to pi, I mean, up to 0.9 pi also, it's okay, but very close to pi, error bars tend to be large. So it's precisely the point where it becomes more difficult. Yes, but that's right. So I think it's a very interesting question to discuss that.
So when you showed there was this plot that goes when it goes to pi, it's still not coming down.
Right.
But I'm just confused with something very basic. That why you are stuck with one branch? Why you're not crossing the branch?
Yeah. So indeed, that's also a good question. And the reason is that that's related to how you evaluate the integral. So in the Monte Carlo simulations, you don't explore all the possibilities because it's too gigantic, but rather extract some sample configurations, which we believe captures the essence, kind of, because it gives the most important contribution. And then the third one is that, strictly speaking, whether what configuration we should choose depends on theta, but also there could be different set of configurations if there are multiple branches. And what I'm doing here is to generate the lattice configuration of theta equal to 0. And I keep using that to do that. So, for example, if you want to see the other branch, like here, I don't think you can see that there because you keep using the same configurations. But partly because I'm using this, precisely because I'm using the same configuration, that's actually a good thing because I can follow the branch. That's my understanding.
So it's related to the question that I asked before. So we know that the two branches support different one-form mathematics. So maybe that's also related to the configurations that you sample. That the configuration on the other branch are preferred if they maybe cancel the SPC pattern. Anyway, we can talk about it.
Yeah, I mean, yeah, in a sense, right. So I think it's interesting. The one thing is that it's not like you have to. I mean, yeah, almost the starting thing is two-part periodic, so it's almost the same configuration, but you have to, yes, wait. So it's not like you have to change completely different thing, but in other words, you can start with this and extrapolate to say like a pi, and then it's like that's like coming here. So, but of course it's a different configuration, and so and indeed there is a factor plus minus sign, etc. coming out, and then that changes, which gives a preferred configurations. And so I think that's the situation, and I wonder maybe there could be a much simpler problem where you can analyze that explicitly yourself, which in the discrete gauge theory or something like that. That could be interesting, but I don't have a sharp comment about that.
All right, let's thank Masahito again. And let's take a 3-minute break.